children. All right, so this word right here you guys may not have seen because it used to be something that we had to do in pre-calculus, but they've taken it out. A function that is even is going to be symmetric about the y-axis, because it tells you that it is even and continuous from -3 to 3. So we have the properties, but they only give you information from 0 to 3. The reason that they do that is because whatever you figure out from 0 to 3, whatever it looks like, it's just going to be mirrored on the other side because it's symmetric about that y-axis. So they only give you the information for 0 through 3, but we could just basically like reflect that from the other side. So we're supposed to find the x-coordinate of each point at which f attains an absolute maximum value or an absolute minimum value. For each coordinate you give, state whether f attains an absolute maximum or an absolute minimum. So for this, I think this table is a little bit hard to read. It also does not include, like it doesn't go from -3 to +3. So these parts right here, these are just the values at 0, 1, 2, and they don't give you 3. All right, so these are the values, and notice they're, except for these two right here, you got zeros or undefined for most of these, particularly for your derivatives. They're all either 0 or undefined, which means that you're looking at critical points there for those values. So if we think about changing this into like a sign line for this, and let's go ahead and make it from, like we got 0, 1, 2, 3. Let's go ahead and make it -1, -2, -3 also. Because whatever we see on one side is going to be flipped and mirrored on the other side. So when we're talking about maximums and minimums, we really care about the derivative being positive or negative, which tells us the function is increasing or decreasing. So we're not going to look at second derivative here. We're looking at, we're just looking at first derivative line right here. And we can, don't worry about the values at the specific points. They are either undefined or 0, which tells you that you have a critical point there. So that just means that number goes on the sign line. So from 0 to 1, we got negative. From 1 to 2, we have negative. And from 2 to 3, we have positive. And so they don't give us the information for this other side. I'm going to kind of put me like a dotted line right here, because they don't give us the information over here. But because this graph is symmetric, we're going to see this sort of just flipped there, right? So let's think about what this tells us. Well, I don't know why. Let's see. Let's think about what this tells us about f of x, right? So if we're looking at this, it tells us here that we'll be increasing, decreasing, 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 increasing. That's not right. What have I done now? This is not right. I think it doesn't flip. Okay, so here's what happens. If we've got a function that decreases, decreases, and then increases, something like that, right? So here would be 1, here would be 2, over here would be 3, right? Decreases, decreases, increases, right? If we flip that over here to make it symmetric, we actually end up with the opposite, right? So I did that wrong whenever I did this. So we would see right here at -1, -2, and -3, we would actually decrease. Let me fix this. Sorry about that. Let's get rid of this. My other side is wrong. All right, so we would see negative here. We would decrease here, positive, positive, so we would decrease, increase, increase. So where could we have a maximum? Maximums happen where we switch from positive to negative on our derivative, which happens right here, okay, at 0. This is a possible maximum. Do we have anywhere else we switch from positive to negative? We do not. But for these, the endpoints are also possible values, right? We see that the endpoints would also be possible values for this. So we would say for this, since, and the reason we consider endpoints is because it's asking us for absolute and not relative. If it said relative, we would just say there's a relative minimum at 0 because, and then state that. So since f prime of x switches from positive to negative, f has a relative maximum at x equals 0. Therefore, the absolute maximum is either at x equals -3, x equals 0, or x equals 3. Okay, is everybody with me there on that part? For this, we can see here, like on this side, from 1 to 2, we have a negative value. 2 is at -2. From 2 to 3, we also have a negative value, right? That's the value of the function, meaning the f is below that x-axis. What is the highest possible value you could have for 3? If this graph is negative from 2 to 3, what's the highest possible value you could have for 3? It could be 0. It could be 0, right? Because from 2 to 3 you're negative, which means that the very highest it could be is 0, or it could be still a negative value, right? So since f of x is negative for I'm going to do this, -3 less than x less than -2, and 2 less than x less than 3. So even though that negative part's not, -3 to -2 is not on our table, we know it would be the case. So since it's below the x-axis, we know that f of -3 is less than or equal to 0, and f of 3 is less than or equal to 0. What is f of 0? It is greater than 0. I'm going to go ahead and put the exact value. It's 1 right here. So f of 0 is 1 right here. So if we know the only possible maximums are at the endpoints and at 0, and we know the biggest we can have on these endpoints is 0, but we know that our value here is 1, then we can assume that f has an absolute maximum at x equals 0. All right, so that only covers our maximum. Now let's think about where we would have a minimum. So looking at that table that I've got there, where do we have possible minimums? At 2, right? Right here we switch from negative to positive. And if we have, and also right here at -2, right? Because of the symmetry of the graph. And in fact, because we know this is symmetric, if 2 ends up being an absolute minimum, -2 would also have to be an absolute minimum. We'd have to have a picture that looks, it's not going to look exactly like this, but where we've got a minimum on each side. But they're at the same level, so they would both be absolute minimums. So we would say since f prime of x switches from negative to positive at x equals 2, f has a relative minimum at x equals 2. The absolute, I should say x equals 2 and x equals -2. The absolute minimum is at x equals -3, x equals -2, sorry, I'm running out of room, x equals 2 or x equals 3. Okay, how do we know that the absolute minimum is not going to be 3 or -3? Very good. So our derivative is positive from 2 to 3, which means that the function increases. So if we're here and we switch to increasing, we can't have a lower value there, right? So, since f prime of x is less than 0 for 2 less than x less than 3. F of x, oh, I'm sorry, it's greater than, not less than. It's positive there. Okay, because we're positive between 2 and 3. Greater than 0 for 2 to 3. F of x increases on 2 less than x less than 3. And that tells us f of 3 is greater than f of 2. By symmetry, we would also say f of negative 2, well, f of negative 3 is greater than f of negative 2. Therefore, f of x has an absolute minimum at x equals plus or minus 2. I probably could have condensed my wording down a little bit there, but this would definitely work. Okay, so questions on that first part. You're looking for the relative maximum minimums based on what switches, but then you also have to consider the endpoints and determine whether or not it's possible for them to be maximum minimums. All right, for points of inflection, what do we need to look at? Second derivative. So let's kind of do the same thing we did for the first problem. Let's just do from 0 to 3. That might be easier. And the second derivative, so this time we're looking at, this line. Ooh, that really marks some stuff out. We've got positive, negative, negative. If I just look at this part of the graph. Positive, negative, negative. And let's think about what this looks like if we're reflecting. So positive tells us what about f of x? We have a second derivative that's positive. What's that tell us? Good. We're concave up here, concave down here, concave down here. So we've got something that is concave up and then concave down, and then I think it ends up looking like this, concave down, because it's increasing on that part. If we reflect this, is it going to have the same concavity, like when we flip that over? Okay. It is, yeah, it is the same. So it's still curved up. The increasing and decreasing is going to switch, right? Because this decreases over here, but it increases over here. But the concavity will stay the same. We could say, or this is probably just the way I do it, since f double prime of x switches from positive to negative. At x equals 1, f of x has a point of inflection at x equals 1. And I'm just going to do this due to the symmetry of an even function f of x also has a point of inflection at x equals negative 1. Those you really just have to think about the sign change. It's a little more straightforward. If they had only asked for relative maximum minimum up here, it would be easier because you wouldn't have to consider like the endpoints there. For points of inflection, you don't have to consider endpoints on that. All right, so the sketch. Okay, this graph gives you coordinates 0, 1, 1, 0 to negative 1. Okay, so you want to graph those 0, 1, 1, 0 to negative 1. All right, so we know we have those points right there. And then basically we just want to look at each section and decide what's happening. So here, negative first derivative tells me I'm decreasing. Positive second derivative tells me concave up. So I'm decreasing but concave up. That's going to look like this between 0 and 1. From 1 to 2, negative tells me I'm decreasing. Negative again tells me I'm concave down. So decreasing concave down looks like this. And then from 2 to 3, positive tells me increasing, negative tells me concave down. So I need positive and increasing. I need to be increasing concave down here. You can do it like this. You could go all the way. They don't give you the value for 3, so you don't know what it is. You could do something like this where it's real low. Or you could go, like, make it, it really doesn't matter. Like, you could go all the way up to where that does equals 0. You just can't cross that line there. So something of this nature, you got a little play in what that last part looks like, but it needs to be concave down. So we sketched the right-hand side. A even graph is just going to be symmetric. So it's going to look, put those actual points in, will help us maybe a little bit. It's going to look like that. All right, questions?